So we touched on this last time, that technology, of course, had a big impact on World War II, but even World War I. In World War I, we didn't know much about the atom, or certainly the neutron not been discovered, but chemical warfare was a big issue in World War I. The Great War was called, a brutal confrontation, trench warfare, 21 million battle casualties, huge carnage. And part of that was chemical warfare. Of course, in the late 1800s, this was forbidden by a treaty, international treaty, that one should not use chemicals in warfare. But the Germans developed that quite robustly. They blamed the French, who started it first. Even the British got into it, and then the Americans. We got into the war later, but then we also developed a huge chemical weapons stockpile. And so that was prominent chemists in Germany. Fritz Haber, who developed the Haber process, a way of doing chemical separations. Otto Hahn, younger than Fritz Haber, eventual Nobel laureate, when we come to the whole story of nuclear fission. But they were crucial in developing chemical warfare for the German military. And that resulted in maybe 1 million deaths by use of those chemical weapons that the world has tried to avoid since. Biplanes. Airplanes were, of course, invented around the turn of the century, and the Germans developed large biplanes that for the first time delivered bombs that dropped on London. So that was another case of technology influencing this war. Machine gun. Machine gun was invented by Americans. Gatling, the Gatling machine gun. That was one of another step forward, a way to shoot people much more efficiently. So, this is trench warfare. Lines of soldiers would attack a front, defending soldiers in a trench. And of course, the machine gun made it much more efficient to mow down advancing troops. So it was an awful war. In the historical survey we've been talking about, of course, the neutron was discovered in 1932. And, this was part of the whole change of the classical physics to the modern physics. Of course, the neutron discovery in 1932 by Chadwick was then key for the technology that affected World War II, that is nuclear fission and the atomic bomb. So that was a big step, understanding that the nucleus had not only a proton, which had a positive charge, but a neutron, which had no charge. And so that was a big step forward in 1932. And of course, that led to understanding for the first time what nuclei are composed of. So after the discovery of the neutron, then people realized that the element is defined by number of protons in the nucleus. Hydrogen is 1 proton, helium is 2, lithium is 3, and so on. And so that determines the element. The heaviest element in nature is uranium, 92 protons. And the proton has 1 positive charge, but then also after Chadwick's discovery, people realized that neutrons also were in the nucleus. Neutrons about the same mass as the proton, 1,800 times heavier than this little electron. It moved somehow in some kind of orbit around the nucleus. And the neutron has no charge. And that brought up the idea that we now understand, well, isotopes. So hydrogen, the universe is mostly hydrogen. And what's not hydrogen is mostly helium. Element 1 and element 2. But hydrogen has several isotopes. The most common hydrogen, this is always in the way. Can I shrink this? Sorry. Oops. Oh well, I'll get rid of it. And so hydrogen, if it has no neutrons in the nucleus, just one proton, and that's normal hydrogen, most of what the universe is. Hydrogen also exists in the form of deuterium, where you have a proton and a neutron. And that is called, that's a small part of hydrogen, 0.015%. And that's heavy hydrogen. Or water is H2O, heavy water is D2O. And that's part of the discussion later on. We'll get to reactors, because now some of the reactors we built in the world use heavy water as a moderator, not just normal water or light water. Also, there exists tritium, which has 2 neutrons in the nucleus. That's radioactive, 12-year half-life. And that's an important issue when we get to fusion and the eventual hydrogen bomb. Of course, carbon is a very important element in the chemistry of life. Carbon is mostly carbon-12, stable, but also you can have carbon-13, which is stable, 1% of carbon. Also, you can have carbon-14, where it has 6 protons, that is carbon, but also it has 8 neutrons. And it's radioactive, it has a half-life of 50 to 700 years. Therefore, carbon dating, when a living organism dies, hi Ray, when a living organism dies, it stops bringing in new CO2 and a new oxygen, and then the cycle stops, and so whatever carbon is in there decays, and decays with this half-life of 50 to 700 years, and so that's how you do carbon dating on formerly living things. And of course, you have uranium. We'll come to. Uranium has a number of isotopes. Uranium is mostly 238. Uranium is element 92 protons. And so it has a different number of neutrons in the nucleus. And so these are the isotopes of uranium that exist in uranium ore in the ground. It's mostly 238. That doesn't fission. And I'm getting ahead of myself. Now we understand it's uranium-235 that fissions. And that's why Ray's Y12 plant was invented, to enrich uranium in this isotope so that you can have to build a bomb. Also, this is uranium-234. So those are isotopes. There are 92 elements in nature. Most are solids. 11 are gases and 2 are liquid at room temperature. Tin has the most stable isotopes. It has 10 stable isotopes. And so there's a lot of different tin nuclei that exist. So that we came to know and understand after the neutron was discovered. We also came to know more and more about the fact that there are 3 kinds of radioactivity. This is what Marie Curie and Becquerel started studying around the turn of the century. There's beta decay, where a neutron in the radioactive nucleus turns into a proton. Emits an electron called a beta particle, also emits a neutrino. And we know that well. So some radioactive nuclei move closer to stability by changing a neutron into a proton, emitting beta particle. Other nuclei that are radioactive, especially heavy nuclei, lose some of their excitation energy by emitting an alpha particle, which is the helium nucleus, which is 2 protons, 2 neutrons. And that's bound together very strongly. And so that's another way for a radioactive nucleus to decay. Or a radioactive nucleus could just emit electromagnetic radiation, gamma rays, a higher energy form of X-rays. And so this is what people like Rutherford and others figured out early in the century. In the late 1800s, Budapest in Hungary was one of the most sophisticated, most beautiful cities in Europe. And in fact, the first subway in Europe opened in Budapest, not in London, or not in Paris. I'm talking about the continental part of Europe, not in Paris or Rome, but in Budapest. So it's a very elegant city, a center of commerce, a center of culture. There were 5% of the Hungarian population were Jewish, but they were the ones that owned 37% of the land and were half of the lawyers in the country and most of the financiers. So the Jewish part of the Hungarian population was small, but it made it really the middle class, or the upper end of the middle class of a lot of professional jobs. Then the Hungarian Revolution occurred in 1918. And after that didn't last long. Then the Hungarian Communist Party was established in November of 1918. And the former Lenin associate came to take the lead on the Hungarian Soviet Republic in 1919. But that was short-lived, 130 days or something like that. And then a strong armed, a military leader took over in the fall of 1919 in Hungary and installed the first fascist government in Europe. And that's when the first laws against the Jewish population in Hungary were installed. One such law was that no part of the population could occupy a percentage of the professional jobs, whether a physician or a lawyer or government official or whatever, beyond their segment of the population. So this was a rather obvious form of anti-Semitism. And so already then in 1919, the Jews lost a lot of the prominent jobs because of this new law that was passed in Hungary. Well, there were a number of special scientists, 7 of which were most notable, who all grew up near Budapest, all came from middle-class Jewish families, all were interested in science. And these are the 7 that we know a lot about in the history of science since the early 1900s. And we'll come across these more and more as time goes on. They were child prodigies. They were middle-class Jewish families. Some of the parents were financiers, some were educators. Von Karman could multiply 6-figure numbers in his head when he was 6 years old to impress friends and family that would visit von Karman's. Von Neumann had a photographic memory. He could recite back, even at his young age, whole chapters of books that he read. His father was very educated, I think a teacher. He conversed with his father at a young age in classical Greek. So just a genius. Teller, one of these 7, was late to speak. Didn't speak at all till he was 3. People wonder if he had a mental disability. But when he started speaking, he spoke in complete sentences. All very smart people. 2 won Nobel Prizes, FSA and Victor. And Szilard, we'll come back to a lot, played a prominent role. Szilard drafted the letter in 1939 that Einstein sent to President Roosevelt about the possibility of a weapon based upon nuclear fission. So each of these, Wigner then was the first scientific director of Oak Ridge National Laboratory after World War II. And my field is physics, so that was cool to me because I had that same job after UT Patel took over management lab. That same job as the director of scientific research at the laboratory. And that's how Victor was at Oak Ridge back in Manhattan Project and the video thereafter. A lot of these people, von Neumann, when Hitler came to power and Jews had to leave Germany, so all these people came to Germany, left Hungary because of the persecution of the Jews in Hungary, came to Germany to do their studies of science in the early part of the century. And then when Hitler was made Chancellor of Germany and started passing the anti-Semitism laws, then they all had to leave Germany, mostly coming to England and the US. So these are, people have joked about this. I forgot to bring the book. There's a book called The Martians of Science.
Martians of Science.
You brought that last time for me to look at. The question was, how could such great scientists all come from one small part of the world near Budapest?
Within a 100-mile radius, I believe.
Right. And of course, they all spoke funny because Hungarian is one of the world's weirdest languages. So they spoke with a heavy accent, trying to speak German or English. And so the tongue-in-cheek answer was, well, they came from Mars. To explain how they were so different. So they all left Hungary in the early part of the century, go to Germany, then later they were driven out of Germany. These are the 7 that have the most prominence. They're all not in fact the same age. Wigner and Teller are the youngest of the batch, except for von Neumann. And Teller then, after World War II, became the person for which Livermore National Laboratory was started in the early 50s in order to develop the hydrogen bomb based upon fusion. Szilard, one of these 7, left Hungary, studied in Berlin for his PhD work. Einstein was on the faculty in Berlin by that time, so he became a close associate of the faculty. He applied for, Szilard was a real entrepreneur, a real smart guy. Applied for 29 patents throughout his career, a lot of them with Einstein back in the early part of the century when he was in Berlin. He got his degree in Berlin in 1933. He got his degree earlier, in around 1921, stayed on the faculty in Berlin until 1933. Hitler was put in prison in 1923. Came out of prison in 1924. We'll come back to this. That's when Hitler wrote Mein Kampf. When he was in prison, when he was released, then things started changing. He became chancellor in 1932. And so after Hitler became chancellor, then he realized that it was time to go. He left Germany, went to England, and then to the US. A lot of inventions. We'll come back to Ernst Lawrence from Berkeley. Got a Nobel Prize for inventing the cyclotron, a way to accelerate charged particles in the magnetic field to do experiments. He came up with this idea actually before Lawrence did, but didn't have the resources to develop this concept and build the first cyclotron. After Szilard left Germany in 1933, he came to England. He became friends with H.G. Wells. H.G. Wells of War of the Worlds fame. You know, the story about the invasion of the Martians on Earth. And so in 1914, Wells wrote this novel, The World Set Free, in which he envisioned a lot of what happened. He envisioned in this novel a war in 1956 between an alliance England, France, maybe America versus Germany and Austria. Well, the timing was off, but it happened. But before that, he envisioned in this novel that a war ended when when the major cities were destroyed by some kind of an atomic bomb. Well, this was 1914, so the neutron had not been discovered. By 1914, Rutherford does an experiment figuring out that there was a nucleus composed primarily of protons, but had to be something else there. So not much was known about the atom, except there was a nucleus, and it must have a lot of energy. So that was part of his novel. And it was just amazing that H.G. Wells had the foresight in his novel to predict things that actually happened. Well, Szilard became friends with H.G. Wells and was intrigued by that book and was a visionary. Szilard was an entrepreneur. So those ideas were in his mind. Those science fiction ideas of Wells were in his mind. As it came to him when he went to a meeting of the British Association and heard Rutherford speak in 1933. Rutherford speaking that the nucleus now, after the discovery of the neutron, had protons and neutrons. It had to be very energetic in order to have that much mass in that small of a volume. And if you could release that energy, you could make a weapon. But Rutherford himself was extremely strong in saying this will never be useful. Even though there's a lot of energy in the nucleus, a very small, very powerful nucleus, it can never be harnessed. Still, after knowing Wells, H.G. Wells, so closely, he then thought about this, and Szilard was probably the first to think, gee whiz, if you could split apart the nucleus that he just heard about from Rutherford in that talk in London, and if when you split apart the nucleus, some of these newfound uncharged neutrons could be emitted, then gee whiz, you might be able to make a chain reaction. And that was just an amazing idea that he had. So he saw into the future that perhaps you could make a weapon if you could find some element that would then break up and emit a few neutrons when it's split up. And he even tried to patent that idea later of a chain reaction. So Szilard was a real visionary, like his friend H.G. Wells. Niels Bohr, we've talked about already a bit. Niels Bohr was the father of the atom, a Danish physicist. He won a Nobel Prize in 1922 for his idea that there was an atom, and the way it was stable was the electrons moved around the atom in stationary orbits where they would not emit energy until they jumped from one energy level to another. And when you have an atom with a nucleus at the center, different orbits with electrons, while in a stationary orbit would not radiate, therefore producing stability. But when an electron jumps from one orbit down to a lower orbit, it would give off radiation, visible, ultraviolet, infrared. And Bohr worked out the model of the nucleus, the model of the atom, that could explain those characteristic X-rays that are emitted when an electron jumps from one orbit to another in hydrogen or helium or whatever. So I got the Nobel Prize in 1922. Well, he was a hero in Denmark, and they built for Bohr an institute, the Niels Bohr Institute in Copenhagen, right next to the Fælles Park, and part of the University of Copenhagen. This place has a lot of meaning to me because it's a place where I have spent 3 years of my life as a nuclear physicist. First, just after I got my PhD for a year, and then 10 years later for a year, and 10 years after that for 5 months, and many summers. So this was the institute built for Niels Bohr in Copenhagen. And it's bigger now, but he and his family lived there. Also, part of the institute was housing, or kind of the German model. The professor lived there, and the visitors, the family all lived in the same complex. And so Bohr was the first to explain that there's a link between the chemistry of the elements and the physics of the elements. And he pointed out that he worked out the model of where the atomic energy levels are, the orbits are. He pointed out, for example, that two very different elements, barium, which has 6 protons, and radium, which has 88 protons, have the same chemistry. And they have the same chemistry because the electrons go into shells, and the chemistry is affected by the electrons in the outermost shells. The electrons in the closed shell near the nucleus do not really affect the chemistry. But Bohr worked out the order of the electron shells. He realized that barium has the same number of electrons in the last few shells as does radium. And then he brought order to the periodic chart, realizing that they have the same chemical properties. And so we understand that now, that this is a periodic table. You have different groups of elements that have similar chemical properties. The newest is 117, Tennessee. It has the same chemical properties as fluorine, chlorine, and bromine, and so on. Group 17, because it has the same number of electrons in the outermost valence shell. Well, that was Bohr who had worked out that for the first time. And now we understand well the periodic table. And it was he who predicted that missing element 73, 72 was not known yet, that it should not be a lanthanide, have the same chemical properties as all of these elements, which have the same outermost electrons. Those are the lanthanides. It will assume that 72 would have the same chemistry as lutetium, terbium, thulium, and erbium, and so on. But Bohr predicted that element 72, when it was found, would be like zirconium in its chemical properties. Well, yeah.
Just an anecdote. Niels Bohr, to show how close that is to us in this room. We were up in an old gentleman who was talked on this week. And Homer Wilkins, he's in Manor House, assisted living home. He said the other day he met Niels Bohr.
He met Niels Bohr.
He met Niels Bohr. He was a Harvard physics major, former professor, and he said he met Niels Bohr.
Where and when?
I don't know the details. That's all I know. But it was close, close proximity to somebody like that.
Yeah. Huh. I get well, Bohr came to the U.S. regularly, both during World War II and after.
Yeah, yeah.
He died in 1963.
Okay, so Homer was born in 1923, so
Yeah.
95 years old now.
Right.
He was a major at Harvard.
Yeah.
And he said he met him.
Yeah. Right. Yeah, I arrived at Niels Bohr Institute in fall of '68 after I finished my PhD work, and Niels Bohr died 5 years earlier. Met his wife, Margareta. We all went to their summer house up in Sicily. His wife was still alive and still hosting the Niels Bohr Institute visitors. But no, I never met Niels Bohr. He was gone by the time I got there. Very nice, very neat. Oh, by the way, come back to this, but it was Hevesy, one of the Hungarian Jews. When he left Germany in 1933, he went to Copenhagen to work at Bohr's Institute. And it was he that found, based upon Bohr's suggestion, that element 72 should have a chemistry of zirconium, And he and his colleagues, the Niels Bohr Institute, started looking at analyzing deposits with zirconium and was able to chemically separate a different one, hafnium. And so that's how element 72 was discovered, because of Bohr's prediction would have the chemistry of zirconium. Indeed, when Bohr was in Stockholm to accept his Nobel Prize, he got the phone call the night before his talk that they just found hafnium based upon his prediction from his model of the atom. So Bohr proudly announced the discovery of hafnium in his Nobel address in Stockholm. Bohr, of course, went off into Germany. Germany in the 1920s was the center of science. He went in 1922 to give to his colleague Arthur Sommerfeld and to give a talk. In the audience was a young student, Heisenberg, Werner Heisenberg. Later on, you know, he became the head of the German Manhattan Project. Heisenberg was 20 years old when he heard Bohr speak. A young physics student, intrigued by Bohr's model of the atom, by the quantum model of the atom, very different from the classical model of the atom. They became friends. They went hiking together. That was Bohr's tradition. Avid outdoorsman. He would love to hike. Heisenberg went for a hike right away in the mountains in Germany, taught physics the whole time. Heisenberg then came to Copenhagen, spent time in Copenhagen with Bohr. Bohr became his mentor, his inspiration in physics. This is all ironic because later on we'll talk about the play Copenhagen, which was performed at UT about, I don't know, 8 or 10 years ago, where during the Nazi occupation of Denmark in World War II, Heisenberg goes to see Bohr, his close friend and mentor, about what was happening relative to developing the atomic bomb in the US. And it was a very tense relationship that ended their lifetime partnership in physics. That's what the play Copenhagen is about. We'll talk about that more later. But Heisenberg really admired Bohr a great deal, worked with him, came to Copenhagen often to talk about quantization of electron orbits. But Heisenberg was a genius mathematician, and Bohr had a lot of intuition in physics, but was not that good of a mathematician. And so that's what Heisenberg brought to this collaboration with Bohr. He was strong in matrix algebra, for example, and used matrix algebra as a way to develop quantum mechanics. We all heard quantum mechanics, there's classical mechanics. You know, that's sort of the way bodies interact at the large scale, planets moving around, stars, billiard balls bouncing off of each other, cars colliding with other cars. Nothing quantal about that. That's the motion of large objects. Heisenberg developed the mathematics of mechanics at the quantum level, the microscopic level, we call that quantum mechanics. And that was very successful in giving the mathematical detail to Bohr's quantized model of the atom. So they had a very close relationship. Well, about this time, Oppenheimer came along. And one of you is going to talk about Oppenheimer. I guess Sarah will talk more about Oppenheimer. Oppenheimer came to Germany in this period too. Oppenheimer was born in 1904 to Jewish parents. Jewish people that left Germany earlier for opportunity came to New York, started a fabric business, became rich in New York City, and had 2 children, 2 boys. The older boy, Robert, was very shy, interested in science, interested in geology and rocks. By the way, it was his early interest in science, but and a complete social misfit. Got bullied a lot in school because he was frail and shy and just strange. Not a good communicator. Also very sickly, because he never got out much. He wanted to stay inside in New York City, in their apartment all the time. So his father arranged for him to spend the summer of 1922, when he was 18, out in New Mexico with a guy, toughen up this kid. You know, he's just so sickly and anemic that he needed to be outside to change his physical capabilities. Well, this comes back later when he was chosen by Groves to direct the Manhattan Project. He knew well New Mexico. He knew well the Mesa, not far from Santa Fe. That's now the location of the Los Alamos National Lab. And so it was Oppenheimer that convinced Groves to put that secret laboratory on top of that Mesa at Los Alamos. When he first visited there for the first time in the summer of 1922, when his father was out there. That toughened him up. He had gotten into Harvard, but was unable to start. But after that experience, he was ready physically and mentally to enter Harvard. He got through Harvard in 3 years. He took a lot of courses. He was a chemistry major, very diverse guy, wrote poetry, learned Sanskrit, learned languages, chased girls, had a great time at Harvard. Just a very bright individual, involved in many things. After Harvard, he decided he would go to work with Rutherford in England, the father of the nucleus. He decided he wanted to focus on physics as opposed to chemistry. But that didn't work very well. He was a terrible experimentalist, terrible in the laboratory, terrible with his hands. And so working with Rutherford was really very difficult. He tried to work with Thomson after Thomson was at the end of his career. After Rutherford booted him out of his lab, he went to work for J.J. Thomson, the person who discovered the electron. But that didn't work either because Oppenheimer was terrible in the laboratory to be an experimentalist. And he had psychological problems. He went to see a psychiatrist then, contemplated suicide apparently, because he was not measuring up to the great physicists like Thomson and Rutherford and others. But he then met Niels Bohr when Niels came to visit Rutherford at one point, and it was Bohr, the Dane, who inspired him to be a theoretical physicist, to work on quantum mechanics relative to atoms and molecules as opposed to try and measure things. And that was the change. And Oppenheimer became a great physicist, almost won a Nobel Prize. And then later on, was chosen by General Groves to be the leader of the Manhattan Project. He went in 1926 to Göttingen in Germany to work with Max Born, a great German physicist. This, of course, is before Hitler came to power. They worked on quantum theory, Bohr and Heisenberg's quantum theory applied to molecules. Published 16 papers in that period, those 3 years. Got his PhD in Göttingen. Of course, then, you had to speak German. Before World War II, German was the language of science, not English. And so before World War II, if you went to Germany to work with these great physicists, you better be fluent in German. And he was pretty good at that. After he got his PhD, he came back to America. He had offers. He could have gone to Harvard to be on the faculty. He decided he would go to California. He took a dual appointment between Caltech and University of California, Berkeley. Well, there was no theoretical physics effort at Berkeley in the late 20s. It was a new university. Physics-wise, it was nowhere. Caltech was new, but advanced rapidly as a great university. Oppenheimer became really the father of the American School of Theoretical Physics, starting in the late 20s with his new position at Berkeley. We'll come back to that. He met various people who were the intelligentsia of the time, dabbled in the Communist Party and so on. And this debate raged, however, the debate between classical physics and quantum physics. Classical physics was the physics of Newton and all that followed him. Newton's three laws. It was deterministic. You knew the position and velocity of every body, every object in the universe. The idea was you could predict the future of the universe. Bohr's quantum physics, Albert Heisenberg, said that it was much different, that the laws of physics at the microscopic level was not deterministic. It wasn't clear when electrons would jump from one orbit to another and emit radiation. Of course, Einstein was famously quoted over the years that he died, God doesn't throw dice. That Einstein, the great Einstein, felt that classical physics had to be the answer, and this new quantum mechanics wasn't really just right. Schrödinger in 1926 played a role in this, published a paper on wave mechanics, saying that you could, in classical physics, treat electrons as waves. But you didn't have to invent quantum orbits for electrons moving around the atom, that you could view them as waves. Wave mechanics, in other words. And that things like emission of light, X-rays of certain wavelengths from atoms, whether it's hydrogen or uranium or whatever, be treated as an interference principle. If you've got two waves, if they got these two waves, they're in phase where the peaks occur at the same. The peaks occur at the same time that they had consecutively. So here, these two are the same. They peak at the same point. You add this wave to this wave, you get a bigger wave, the same wavelength, same frequency, just a bigger amplitude. Or if they're out of phase, one of them peaks as the other has a valley, then they're out of phase. When you add these two waves together, then you get interference. Well, that's because of wave properties. Light is like that. Light has interference. And Schrödinger said you could explain everything by wave mechanics. The emission of light would be interference of waves. You didn't have to involve quantized orbits in this new quantum physics. So that was a huge debate that went on. Heisenberg was a Bohr colleague. Said, how do you rectify this? Wave mechanics versus quantum mechanics. Two very different views of the universe. There was a famous physics meeting at Como in Italy where this was debated. Einstein was there, and huge debate. Heisenberg then came to Copenhagen after the Lake Como meeting in 1926, I believe, and worked on this conundrum. How do you know? Is it wave mechanics, waves interfering, or quantum orbits for electrons? And it was Heisenberg that made the huge step forward by saying that there's an uncertainty principle. mathematically, this is the uncertainty principle for which Heisenberg got his Nobel Prize. Where what it says is that there's uncertainty in measuring the position of an object, and there's uncertainty in measuring the momentum or the velocity of an object, and that's related to Planck's constant, it's very small numbers. And what this means is that you can never know precisely the position and the velocity of any object. Now you can, if it's a car speeding along, you use radar to measure the velocity, and that radar wave does not change the pathway of the car. You can photograph where the car is, so you know precisely where that automobile is and how fast it's moving. But if you're talking about an electron, it doesn't work that way. To probe an electron, you have to, you've got to affect it somehow. The electron is that dime. If you probe it, I can't see it. I have to then touch it to see where it is with some instrument. Well, if I touch it, I move it. Or if it's moving, I try to touch it, then I change its velocity to know where it is. So the point is that when you measure anything, like the dime on the table, if it's really small, you change it, or you cannot know precisely its position and its motion. That's the uncertainty principle that rules at the microscopic level, at the quantum level. You published that paper, got a Nobel Prize, and then Bohr at the same time developed this idea of complementarity, that there's a complementary relationship between classical physics and quantum physics. Classical physics works at the macroscopic level, planets, cars, baseballs, tennis balls. But as you go smaller and smaller, you get a complementary set of rules and laws of physics, quantum physics, and one blends smoothly into another in a complementary way. And Bohr and Heisenberg worked that out. And that's how Heisenberg got into that problems. This was all debated still in Germany. Heisenberg was called a white Jew because Heisenberg dared to espouse this newfound physics that was being pushed by mostly Jewish physicists. And this affected Heisenberg for years. The Jewish physicists had to leave Germany after Hitler took power. Hans Bethe, many others. And the fact that Heisenberg espoused the quantum physics made him be labeled, even among German physicists, more elderly German physicists, as a white Jew. And so the SS, when he was being considered to lead the German version of the Manhattan Project, the SS quizzed him a lot, looked at his background, because he was suspicious, because he had wrapped his arms around quantum physics. Hard to believe, but that was viewed as Jewish physics. Einstein, another example, the prime example of the Jewish physics. Einstein was Jewish, born in Germany in 1879, grew up in Munich. Once again, slow to speak as a child. Father was a businessman, but not a very good businessman. His business often failed. They moved to Milano in Italy, then to Zurich, Switzerland. He renounced his German citizenship in 1901 over these early problems for Jews in Germany. He then got his degree, was a terrible student, got his degree, worked in the Swiss Patent Office in Bern, in Switzerland, from 1902 to 1909. And while he was working his day job in the patent office, he published in 1905 4 physics papers that changed the world of physics. This is remarkable. This is called the miracle year, because he published 4 papers that really changed the landscape of physics, and of course affected a lot of what was to come in the world. We mentioned a little bit earlier the Nobel Prize in 1921 for the photoelectric effect. Special relativity was published. E equals mc squared. This is how you can figure out how much energy uranium gives off when it's fission, because of E equals mc squared. M is the mass of material that is given off. E is its energy. C is the velocity of light. Well, these are 4 papers he published in 1905. After that, his first visit to New York in 1921, he got a motorcade. He was the rock star of science in the world, Einstein. He published special relativity and general relativity. Special relativity published first, 1905, general relativity, 1915. I want to tell you a little bit about those. I'm not trying to make you a physicist, but just to give you a broad understanding of how different this was, how it affected the world. Special relativity said nothing would travel faster than the speed of light, independent of whether you're moving or stationary. General relativity has more to do about the curvature of space related to intense gravitational fields. He received a Nobel Prize in 1921 especially for the photoelectric effect. But he predicted also that year, in 1915, he published general relativity that said that space is curved, that when you're near a star, gravity, of course, is attractive. You know that if you have a large star and a small planet, that there's a gravitational force between them. That's why the object moves around a large body, the gravitational force. But his point of general relativity is not just that planet with mass that feels the gravitational force of the big star. It's that all of space around here is curved. The space. The space is changed by an intense gravitational field. Well, that produced a possibility to verify that. In 1919, there was a total solar eclipse that was predicted to be visible off the coast of West Africa. Einstein predicted in 1915 that space was curved. How do you verify that? A very radical proposal. Well, Arthur Eddington mounted an expedition to go to an island off the coast of West Africa to observe that total eclipse in 1990 to see if starlight would be affected by passage near the sun. In other words, you see, you're out here on Earth and you have an eclipse of the sun. Normally, these two stars would be separated by this amount. No. By this amount. Two stars in the sky behind the sun. That light, pulse of light from that star, when it passes near the sun, Einstein's prediction says, it would be curved. Because of the intense gravitational field of the sun, the pulse of light has no mass, so it can't be attracted by the sun, but if space is curved, then that pulse of light moves along that curved line of space. And this pulse of light from this star, so that if you could see those two stars behind the sun, therefore in an eclipse condition, these two stars that you know are that far apart would appear to be this far apart. Because space near the sun is curved. So that's what Eddington did. He knew the eclipse was coming. He knew what stars would be there in the star field behind the sun. The eclipse occurred so that the sun was blocked out. And Arthur Eddington measured that during an eclipse, when those pulses of light from those two stars passed near the sun, they curved. And their position was apparently different from that vantage point. Well, then Einstein became a rock star. That's when he visited New York in 1921. He got a hero's welcome because this experiment made him instantly famous. And so that's general relativity, that space near a heavy gravitational field is curved by the gravitational field of that star. Now, you've probably heard about gravitational waves. This was discovered in the last 3 years. I never thought in my lifetime that this would happen. But in 2015, gravitational waves were found. In other words, now we know space is curved, but Einstein also predicted that there should exist gravitational waves that went out through the universe due to a sudden gravitational event. So if you have two objects, two black holes, two neutron stars, whatever, suddenly collide, but that momentary collision produces a ripple in space-time, such that you should have them traveling out beyond a gravitational wave. So you've got not only a space curve, but you have suddenly a collision of two massive stars, neutron stars, whatever, then there'd be a ripple in that curvature of space that would proceed out forevermore. And that's been a prediction ever since Albert Einstein. Never observed. I thought that will never be observed. Not in my lifetime. But it was observed. And this will win a Nobel Prize soon. The LIGO project was in this country funded by the National Science Foundation. There's two big detectors, one in Louisiana, one in the state of Washington. Both are interferometers, where you take a laser, you split the beam, bounces off this mirror, comes back, reflected to the detector. The same light is sent to this mirror, comes back, and is combined then. So light is split part of the laser here, then recombined after they bounce off the mirrors in 90-degree directions. Such that if a ripple in space passes through where this detector is, let's say in Washington or Louisiana, you have a very small change in one of those arms. And this is so sensitive, it can detect a change in the distance due to that ripple that proceeds in space of the size of 1/10,000th of the diameter of a proton. And that's why I thought it would never be detected. Well, it was detected. Just a remarkable experiment. See, that's the LIGO detector in the state of Washington. It's 2 miles from each way. There's a similar one in Louisiana. So we got two similar detectors. The neat thing about that is you can see you get the same ripple space-time, can also tell what's coming from there and there and there, where the sky is coming from. And that was detected. That was detected first in 2015, and then a couple more last year. And so,
You said the ground shaking.
no,
What others when you're
because space is curved. That ripple in space, you know, space is curved, but then it's not curved permanently. And that wave started from that collision 1 billion years ago, has been traveling through space. When those two neutron stars collided 1 billion years ago. And so it's space that changed a little bit. The Earth doesn't move. And so one of those arms changes its distance because space curvature has changed. Right.
little Louisiana one.
Well, or one arm at Washington compared to the other arm. And that's the interferometer. Where one beam comes out, comes back, they recombine, and you get a interference, no signal or strong signal. So normally, if there's space-time is the same all around, the two waves going out and reflect off mirrors, they come back, they combine, there's no signal. If you perturb one of those arms by a fraction of the diameter of a proton, it comes back out of phase, and you get a signal. And you see the same signal in Louisiana. It's just the most remarkable thing I've ever heard. Except for UT winning the national championship in 1998. I should tell you more of the Einstein story later, but I wanted Ray Smith to tell the story about hafnium and Y12. Want to do that now, Ray?
I'll be glad to. This story started in 1950 when, can you pull up that
Yes,
image for me
I can.
of 9211? It started in 1950 when, after I actually started in 46 when then Captain Rickover came to study at Eugene Wigner's first nuclear reactor school at the Oak Ridge National Laboratory. And he figured out you could make a small enough reactor to go in the submarine if you used highly enriched uranium. But in the process, by 1950, they had determined that they needed to protect that uranium in the reactor, and they needed to use zirconium to coat the uranium in zirconium. But they couldn't use zirconium as it formed in nature because it had an impurity. That impurity was heavy. So they wanted to separate that impurity out and get pure zirconium. So they did that in building 9211. Now, just a few years ago, no, I hope it's very last.
Yeah, well, I gotta convert that file. I'll do it on this computer because it's a different version of Keynote turns out on this computer. But keep talking.
Sorry, okay. So a few years ago, the man came back that actually did that separation, came back to Whitewell on a tour. I put him in a van. He was Dennis Patt, and he was the head of engineering for the Martin Marietta Energy Systems. The Energy Systems had all 5 of the plants, the 3 here in Oak Ridge, the Paducah plant, the Fort plant, the gaseous diffusion. So it was a large organization. Dennis was a tough manager, a well-respected manager, but back in his early days, he was working in building 9211. So when he came back in, he knew that we were tearing buildings down. He said, Ray, is building 9211 still standing? And I said, yes, sir, it is, but the outer walls are falling off of it. It's going to be going down soon. He said, well, I'd like to see that building before it's going down. So if you would drive me by. So I did. It's over in the biology area, 9211 sand right beside 9210. 9210, or very near. 9210 is what's known as the Mouse House. That's where the violence was here. But in 1950, finished work then, building 9211. And he told me as we were driving by, he says, Ray, you know, we had to pull up on that roof regularly and clean off the dead birds. I said, oh, he said, yes. Part of this process used phosgene gas. And we would emit out the top through stacks out into the atmosphere. And birds flying over would literally fall dead from breathing that gas. So he said, when we were working in that building, we had to protect ourselves against phosgene gas. The way you do that is you wear a respirator. He kind of smiled at the point when he died and said most of us didn't want to wear a respirator.
Ray, move over here so I can see on the camera for sure.
Oh, I'm sorry.
Yeah.
You got it?
Yeah.
So most of them didn't want to wear those respirators. So what they would do is they would figure out what they were going to have to do inside 9211. And they would decide how we're going to do it, and then they would determine who's going to do it this time. And by whatever method they used, one of the individuals would then open the door, take a large breath, hold his breath, go in and make the adjustments that they needed to make, and then come back out before taking the breath. And that way they didn't expose themselves to the phosgene gas that was strong enough to kill the birds flying over. So he told me that story, and that was a neat story. There's a little bit of a follow-on to this that's not humorous at all. It's a tragedy. The follow-on is that in after they finished working for 1 year, 1950, they packaged that up. They had all the zirconium they were going to need. So they had it in finely divided powder. They had barrels of it. There was a lot of it. And they needed to keep it underwater because it was subject to explode. And they wanted to protect that and keep it underwater. So they moved it down to the west end of the plant, stacked it all up in these barrels. And in 1956, a maintenance crew, now thank you, this is building 9211 here. And the wall was falling off here. But that tall building and those smokestacks coming out is where they were finding those dead birds. So at any rate, they moved that zirconium down to the west end of the plant. In 1956, a maintenance crew was standing in their morning session just to talk about what they're going to do today. They were out there leaning on those barrels. Now, they don't know exactly what happened. Maybe there was a fork truck there, maybe there was a spark, but in some fashion, that zirconium that water had evaporated to the point that it was powder now. And it was exposed to the air, and a spark may have set it off. But it exploded. That zirconium exploded. It killed 2 individuals and blew the arm off of the 3rd individual. Now, just about maybe less than 10 years ago, I had a gentleman that worked with my wife over at the Oak Ridge Associated Universities. Said to me, said it through Fanny, said, tell Ray that I've got a letter I want to write him. I want to give to him about zirconium. I said, well, sure, I'd love to have it. So when they brought me the letter, what it was notation that had been taken by this gentleman when his father was on his deathbed. And his father said, I'm concerned about that zirconium, and I want you to take this information and give it to Wycliffe. And what he wanted me to know is that his father was the supervisor over that crew that had 3 people, 2 people killed and 1 injured. So what he said in that letter is he actually wrote down the distance from the road that's known as 7th Street and the actual number of feet that you would find that buried zirconium. And he said what happened is when they started to try and clean that mess up, that generated another explosion just trying to move it. So he said they buried it there. And what he wanted Wycliffe to know is don't dig in this place where this zirconium is. So he noted it.
I took that letter, gave it to the engineering. They know where that spot is. We all doubt that there's really zirconium there because the engineering story is that they actually dispose of all of the zirconium by igniting it, by burning it, by letting it explode in a controlled way. But that supervisor thought they buried it, and he wanted us to know not to dig it in that particular part. So that's the hafnium separation from zirconium storage, the little add-on in the 50s, and how it happened to me was sitting in a video patent and the supervisor, the man who had those people that got injured. Yes, sir.
Ray, do you know why they chose zirconium to clad the uranium?
I do not. I don't know that technical detail, but I do know that it is continued to be used. In some cases, they use aluminum now to clad. Yeah, to clad the material. But I think it's to keep it from oxidizing, to keep that material in a contained cylinder, if you will, when it goes into the reactor. I'm not sure why they're coming. Now, again, when they shipped the uranium-235 out to Los Alamos, they put it in gold line coffee cup size containers. There's a story with that too that we'll tell later. But the reason for that is that it would not mix with the uranium gold state. So it wouldn't. I don't know if zirconium has that same kind of attribute or not.
I think it's a temperature.
They don't.
It's a zirconium alloy, but you need to withstand the temperatures that you get in a reactor. And also it has to not oxidize when you have it in water. So I think it's just mainly thermal properties. But of course, you know, they're looking for a different cladding because if you have a fuel rod that melts, isn't cooled, then even the zirconium cladding can rupture. And then you have hydrogen emitted in that chemical reaction when it gets oxidized. And that's what happened at Fukushima. You had hydrogen vented that blew off the roof of one of the reactor buildings. Very good. Any questions or comments?